Our project is the anti-sleep system for drivers. I am Syed Hossain, Mohammed Al-Qasemi, Arjun, Pragyan, Mainali, and our faculty supervisor is the one and only Dr. Pragyan. So the problem we set out to solve were people falling asleep while they're driving cars. There's 100,000 sleep-related accidents that occur annually. This accounts for 20% of all crashes on the road, and it results in $12.5 billion in losses. More importantly than money, though, 1,500 people are killed yearly, and 71,000 people are injured because of sleep. Therefore, we need to build a system that can correctly and reliably detect the onset of sleep, and once you've detected it, alert the driver just as fast, or faster. To detect sleep, there's a number of different methods. Your heart rate goes down, your blood pressure goes down, your muscles start to relax. But the thing with these is, when these occur, you're already sleeping. So if we detect these things, it's too late. You're in an accident. So what really we can do is observe the face and the eyes, and also hypnic jerks. Hypnic jerks are, I'm sure all of you have done it. Some of you are doing it right now as I do my presentation. What happens is, your head kind of falls and you wake yourself up really quick. So those are the two sensing techniques we're going to use. So this leads us to our system, the anti-sleep system for drivers. It consists of a closed-eye detection sensor, which is a camera connected to MATLAB. The camera keeps taking images of the driver, sending it to MATLAB. MATLAB will check for how long the eyes were closed in the image, and then turn on an audio file to alert the driver to wake up. There's also a head movement sensor, which Mohammed will get into. He'll explain that. I'll explain the closed-eye detection process and how that works. This is a flow chart for it, but the basic idea is MATLAB will get an open eye reference image from the camera. Then it'll keep getting other images after the open eye reference image, and it'll compare it to that original image. If it's very different from that open eye image, then the sleep counter will go up. Once the sleep counter reaches 3, which is 3 seconds, it'll alert the driver. So that means if your eyes have been closed for 3 seconds, it'll alert the driver to wake up. Frame acquisition was the easy part. You just call, it's one line of code to get a frame from the camera. The problem that we faced, which caused our system to be a prototype rather than a ready-to-use system, was the processor speed. On a 2.1 gigahertz laptop that I was working on, it takes 4 seconds to process each frame. On a 2.8 gigahertz desktop, it took 1 second. 4 seconds is definitely not acceptable. It takes about 7 seconds to get in an accident, so we have to alert you 7 seconds before the accident actually happens. 1 second, it's not real time, but we can work with it. So once we get the frame, we use face detection in order to get the eyes. We are amateur image processors, I guess you could say. So we took Mikhail Nielsen's open source code for successive means quantization transforms to detect the face. So what it does is it looks at it at different quantized levels to pick out certain patterns to detect the face. Once you detect the face, we split the face into 3 parts. We take the top third most part of the face, and that's where your eyes are hiding. And then what we spent a lot of time on was figuring out how do you detect that your eyes are closed. The working method is what we call the sleep index method. Go right here. So once you have that eye area image, we grayscale it, and in MATLAB, any grayscaled image is a 2-dimensional matrix with elements ranging from 0 to 200. Elements closer to 0 is a darker black color, closer to 200 is white. So what we do is we take the average of each of those rows and we plot it. Once you plot it, you all get this graph right here. You get 2 maximums and 2 local minimums. We don't really care about the maximum, what we care about is the minimums here. The first minimum you see is due to the eyebrows, because they're dip in the plot because it also turns out darker than your skin. And the second minimum is due to the eyelashes and the pupils. So if you're looking at both of the images, you'll notice that the distance between those 2 minimums is shorter when your eyes are open, as compared to when they're closed. So what we do to figure out if it's closed is we just take the difference between those 2 distances, compare it to a threshold, and now you know if your eyes are open or closed. This is application of our system. So this is the reference image. So MATLAB will go get this picture first. It'll stay like this, and then it'll keep changing these bottom 3 frames. So it'll keep checking for new frames. Again, this takes 4 seconds. It delays. Those 3 pictures will come out 4 seconds after the first one. You'll notice that in the video. This is an illustration of how the program works. So we set the threshold at 5. It was 5 when we tested on ourselves. Anything above that threshold is your eyes were closed. As you can see, if it's just 1 frame where it was closed, you can say that was a blink. If it's consecutive frames, that means your eyes were closed for a number of seconds and you're probably sleepy. So that's when we need to wake you up. And I'll give it to Mohammed to show you how the proximity sensor works.
Okay, the basic idea here is that there is a head movement associated with falling into sleep, like this shown here in the image. MATLAB actually fails to detect the closed eyes. MATLAB is actually optimized to detect the closed eyes when the head is in the upright position. So in these positions, the MATLAB will actually fail to detect the closed eyes. So to compensate for this problem, we had to come up with another tool to detect the head movement. We came up with this tool, which is an ultrasonic sensor. We had to use 2 ultrasonic sensors, one positioned in X direction and one in Z direction with respect to the driver's head. It measures the distance between the sensor. The first one measures the distance between the sensor and the driver's forehead. And the second one measures the distance between the sensor and the left head side of the driver. We had to position the sensors in this way so they detect and actually track any head movement in the forward direction, sideways, or even diagonal. So the sensor we're using actually uses a 5-volt DC, 30 milliamp current. It communicates using a TTL buses. It has a 3-pin, a power, a ground, and a signal pin, which is input and output. It operates in between 0 and 70 temperature. It also has a range between 2 centimeters to 3 meters, which meets our design requirements. So here, how it works. This is the communication protocol. Microcontroller will send out a pulse, shown here, of duration of 5 microseconds typical. Then the sensor will go into an echo hold-off mode about 750 microseconds. In the last 200 microseconds, the sensor will actually send out a pulse into the external environment. Then it's going to receive an echo in a time frame between minimum of 150 microseconds to maximum of 18.5 milliseconds. And this actually corresponds to the specification range, 2 centimeters to 3 meters. So in our design, we try to test it by setting the sensor number 1 in 50 centimeter range, and this is the echo time we got. Sensor 2 in a 25 centimeter range, and this is the echo time we got. In calibrating the sensor, we actually did 2 trials, and we took the average in the desired distance, about 50 and 25, and this is how much accuracy we got. Pragyan will talk about programming the microcontroller.
The main job of the microcontroller here is just to detect the nodding of the driver and then turn on the alert device. For our project, we have picked up Arduino Uno board. It's based on 8 mega 328 microcontroller. Some of the features of the microcontrollers are 16 megahertz clock frequency, and it has a flash memory of 32 kilobytes. And one of the more useful features is the power consumption, which is 200 microamps when it is active, and it's just 0.75 microamps when it is in the sleep mode. And one of the main reasons why we picked this microcontroller is it is compatible with MATLAB. Actually, MATLAB has a package for this particular microcontroller. And comparing this with one of the major microcontrollers that most of us use, which is the 447 is that cost us $100 for the microcontroller plus $100 for the debugger. That's $200. This one costs just $30, and this meets all the requirements for us. And the microcontroller can be powered in 2 major ways. One is using the USB cable connecting to the computer, and another one is an external device, which can be either a 9-volt battery, a car charger, or any AC to DC converter from your wall. This is the schematic of how the sensor and alert device is connected to the microcontroller. Now let's go a little deep into the logic of the logic of the code. What it does is the microcontroller sends the trigger pulse to the sensor, and once the sensor gets the trigger pulse, it sends out an ultrasonic sound towards the object. At the same time, it sends a high signal towards the microcontroller. Once the ultrasonic sound hits the object, comes back to the sensor terminates that high signal. Now the microcontroller is supposed to calculate the length of that pulse, and based on that it will calculate the distance of the object. And if the distance is lower than a certain threshold, it will turn on the alert device. But now we have a problem. How do you determine the threshold? Because all of us don't drive in like from the same distance from the sensor. Some of us, we like to drive closer to the steering wheel. Some of us, we are way back. So the simple solution for that is we let the user define the default position. Unlike MSP430, the board does not have a button on it, so we have implemented an external button. So when the system is powered on, the user presses the button, and the distance at that moment is determined to be the default distance, and that will be the threshold for our system. And once the microcontroller determines that the user is nodding, it will turn on the alert device. And the turning on is a simple driving the pin to high. Now to discuss into like how the signal is more interpreted and how the alert device works, I'll hand it over to Pragyan.
Thank you. Now the alert device is simple but yet useful. We talked about the motion sensor, we talked about the proximity sensor and the microcontroller. Now once the closed eyes are detected, we needed a way to send out a signal. To do that, we simply had a vibrating motor that was powered independently with a 3-volt power supply. And we used the transistor as a switch, and the input to the transistor came from the microcontroller. The microcontroller controlled when to turn on and when to turn off the motor. And also we used the flyback diode to avoid any voltage spikes, because there were inductance in the motor, and to avoid those hazard situations, we used the flyback diode to stabilize the alert device. This is the actual buildup of our alert device. There's a power supply, a microcontroller, and the buzzer connected to it. And the system integration, my partners have talked about, the MATLAB program, the sensors, and the microcontroller controlling it. We're going to now play a short video of our device actually working. Just play.
You'll notice the 4-second delay in here. Or either open the IO or one out.
That's the sound alerting the driver.
This alternate design we had, we wanted to connect MATLAB to the microcontroller.
He's not praying, he's testing to see if the proximity sensor works or not. And so praying for it to work. The speakers are low, but the buzzers are going off.
Sound them.
Yeah, these ones.
There's a second set of sensors.
Yeah. So every time he nods, the motor goes off. And this is the whole system in action if we put it in the car.
Only have one sensor?
To test it out, yes. Yeah, the sound didn't come off, but as his head nodded, the buzzer went off. Results, we tried the closed-eye sensor program, 3 trials. There were 3 trials of those, and 50 frames were processed in each trial. Given the 4-second delay, it ran for 200 seconds. And out of 200 seconds, the closed-eye detected that there were 21 instances where the eyes were closed, but in fact, it was actually 17, 22, and 13, respectively, that were closed, with an average response time of 4.2, 4.1, and 3.8 seconds, respectively. And the efficiency of the math lab program was at 80.26%. These are the total funds spent with all the parts. Parts were $129.51, and the labor cost at 425 total hours, calculated at $30 per hour, was at $12,750. Syed was responsible for the closed-eye sensor program, where Mohammed was responsible for the proximity sensors. Arjun was responsible for the microcontroller, where I was responsible for the system integration and the alert device. And there are many lessons to be learned, but most importantly, we have to make sure that there's always plan B, C, and D. Initially, we started off with a IR LED, sending a infrared beam to the eyes and getting the information back. It was not too safe to be tested on humans, so we had to modify our project, and that took a bit of time. But yeah, at the end of the day, we got it done, but that's all that matters. And we're done with our presentation.